Continuing with section 3.6, let's look at example 3 for some examples of finding the equation of a slant asymptote. For part A, we have f of x equals x cubed over x squared minus 1. First of all, notice the degree of the numerator is exactly one more than the degree of the denominator. So in such a case, you should be able to find the equation of a slant asymptote. The way that we're going to do that is to do a division. X cubed over x squared minus 1 is the same as x cubed divided by x squared minus 1. Since our divisor, x squared minus 1, is not a linear divisor, it's not a first degree polynomial, we have to use long division here, but it's not too hard to do. So take x cubed and divide by x squared minus 1. Now, we want to get x cubed, so we multiply x squared by x. And then we also multiply x by minus 1. That gives us minus 1x, minus x or minus 1x. Now, let's write our our numerator, x cubed, as x cubed plus 0x, so that we can see what happens upon subtracting. Remember, when we do long division, we subtract. So the x cubes cancel. But what we'll be left with from the x terms is 0x minus 1x. That is 0 plus 1, or 1x, or just, in other words, x. So here our quotient, our q of x, is x. The divisor was x squared minus 1. The remainder is 1x, or just x. So we want to write f of x as quotient plus remainder over divisor. So in this case, that would be x plus x over x squared minus 1. Notice the quotient and the remainder are both x in this case. So x plus x over x squared minus 1. It is the quotient that we paid attention to here in terms of the equation of the slant asymptote. The quotient will determine the equation of the slant asymptote. The remainder over divisor part, as x gets large, either approaching large positive values or large negative values, that will shrink down to 0. So the graph will look more and more like the quotient q of x. So the equation of the slant asymptote would be y equals the quotient, which is x. Y equals x. So that's just a straight line passing through the origin. And that is going to be the slant asymptote of the graph. On your graph sheet, the graph of the function in example 3a is shown right here. And you can see the line y equals x acting as a slant asymptote. Notice that the graph, as x gets larger and larger in the positive direction or in the negative direction, the graph gets closer and closer to that diagonal line. So the graph looks more and more like a straight line as you go out to the right or out to the left. I'll also just point out with this graph that it has two vertical asymptotes, and I will show you those when I return to the other sheet, the main set of notes. I'll show you that. So you have two vertical asymptotes. There's one other thing I want to point out. If you look carefully, this graph has symmetry about the origin. This is actually an odd function, and there's actually symmetry about the origin. It's kind of an interesting looking graph. It has kind of an interesting, nice symmetric shape, and that's due to the fact that the function is an odd function. I mentioned a moment ago that the function in example 3a has two vertical asymptotes. The vertical asymptotes would be obtained, as we talked about previously, by setting the denominator equal to 0 and solving for x. If we do it this way, perhaps x squared equals 1, x equals plus or minus 1. So you actually get two solutions there, x equals positive 1, x equals negative 1. And that's why this particular function has two vertical asymptotes, one at positive 1, one at negative 1. Neither of these values will cause the numerator to simultaneously be 0. So both of them will represent vertical asymptotes. For a second example of finding the equation of a slant asymptote, let's look at example 3b. G of x equals negative 2x squared plus 5x plus 1 over x minus 1. If we compare the degree of the numerator, which is 2, to the degree of the denominator, which is 1, we see again the degree of the numerator is exactly 1 more than the degree of the denominator. So that would indicate that a slant asymptote should exist for the graph of this function g of x. So to find it, we need to do a division. However, because the denominator has the form x minus c, we can actually use synthetic division to do the division here, rather than long division. Now you could use long division if you want, but it's not always necessary to use long division to find the equation of a slant asymptote. So here let's try synthetic division. So I'll write the coefficients of the numerator, negative 2, 5, and 1. And then I'll use 1 from the divisor. It's x minus 1, so I use positive 1 up in the left-hand corner. I'll make my little L thing here. Bring down negative 2, multiply, add, multiply, and add, and separate off the last value there, the 4. And basically what I've shown then is that when I do this division, the quotient, which is determined by the first two numbers in the bottom row, this is q of x, the quotient is, remember the degree is 1 less than what you started with when you do a synthetic division. So it was a second degree polynomial that we divided into. The quotient therefore should be first degree. Negative 2x plus 3 plus the remainder is 4, and the original divisor was x minus 1. Well, it's this quotient, negative 2x plus 3, that represents the equation of the slant asymptote. However, in writing the equation of the slant asymptote, we need to write y equals negative 2x plus 3. It is the equation of a line after all, and the equation of a line, a non-vertical line, is y equals mx plus b. So you should write your slant asymptotes in exactly that form. You don't just write negative 2x plus 3. You should write y equals negative 2x plus 3. So we can find the equation of the slant asymptote by doing a division, but in this case, it's easier to use synthetic division. Here's the graph of example 3 part B, and you can see there's a slant asymptote there, and the equation of that line is y equals negative 2x plus 3, which is what we showed previously. You can see that it's a line with a negative slope. It's falling from left to right. It should have its y-intercept at 3, and you can see that is apparently the case. So it's a line with slope negative 2 and y-intercept 3. You can see that as the graph goes to the left, and to the right, it's approaching in both directions that, that slanted line. Notice also there is a vertical asymptote at x equals 1. I'll go back in a moment and just verify that. One thing I want to point out for both of the examples in example 3 is that there is no horizontal asymptote. You can have slant asymptotes along with vertical asymptotes, but slant asymptotes and horizontal asymptotes never occur together with a rational function. And I'll just point out here again in example 3b, if you look at the denominator of x minus 1, if you set that equal to 0, you get x equals 1, and that is the equation of the vertical asymptote that I just pointed out in the graph of this function g. So two observations now that we can make about asymptotes of rational functions. First of all, the graph cannot have both a horizontal asymptote and a slant asymptote, which I just pointed out a minute ago. Slant asymptotes require that the degree of the numerator be greater than that of the denominator, and when that occurs, you cannot have a horizontal asymptote. The second observation, the graph of a rational function can cross a horizontal or slant asymptote. In fact, the graph can even completely coincide with a slant asymptote, intersecting it practically at every point. But it can never cross a vertical asymptote. So the graph can cross a horizontal or slant asymptote, but never cross a vertical asymptote. It can't cross a vertical asymptote because vertical asymptotes only occur where the function is undefined. So if the function is undefined at a vertical asymptote, then there's no way that you can have a point on the graph associated with the value of x at which the asymptote occurs. So you never see graphs cross, you never see the graph of a rational function cross a vertical asymptote. Now a quick application of rational functions and horizontal asymptotes. Example 4 says, upon the introduction of an agent that inhibits growth, the population p in thousands of a colony of bacteria at time t in hours is given by p of t equals 8t plus 16 over 2t plus 1, where t is greater than or equal to 0. Part A says find the initial population of the colony. That would be the population at time 0. That would be p of 0. If we substitute that in, it's 8 times 0 plus 16 over 2 times 0 plus 1. That would simplify to 16 over 1, or 16. That would correspond to 16,000. Since population is measured in thousands, 16,000 bacteria. That's the point that we see right here. Notice how the population is going to crash from that point and start to approach a horizontal asymptote. Part B says to describe the long-term behavior of the population. What we could say here is that as t approaches infinity, that is, as t gets larger and larger, this would be time, this is of course population here, you can see how the population is approaching 4,000. P of t is going to approach 8 divided by 2, or 4. And that's because the degree of the numerator is the same as the degree of the denominator. Both of them are 1. So the population is going to approach it will level off at 4,000 bacteria. So here the occurrence of an asymptote at p equals 4 indicates a leveling off of the population after it is initially decreasing quite rapidly.